A 5 kilogram box is pushed up a 30-degree frictionless ramp, starting from rest at the bottom to a final height of 16 meters by a constant applied force of 30 newtons that's parallel to the ramp, as shown in the figure. So calculate the work done by the applied force as the box is fully pulled up the ramp. And we know that the work done by the applied force is going to be equal to the applied force times the displacement. Since the force is in the same direction as the displacement, the angle between them is 0, so the equation just simplifies down to this: force times displacement. And this one we already know both these values. The applied force is the 30 newtons, and the distance up the ramp you saw for in a previous question using some trig. Since the height of the ramp was 16, it turns out the full length of the ramp, when it's a 30-degree ramp, is 32 meters long. It's double the height. So we can do 30 times 32, which gives you the 960 newtons. This time the work from that non-conservative force is positive because it's increasing the overall total mechanical energy of the box, as opposed to like friction or air resistance, which decreases the mechanical energy. So in part 2, if the work done by that applied force increases the total energy of the box, we're going to use conservation of energy to calculate the speed of the box when it has reached the top of the ramp. So the conservation of energy equation is going to be the E initial plus the work from the non-conservative forces, which in this case is the applied force, is equal to E final. Same equation we've been using. This right here, this work from the non-conservative force, the conservation of energy part comes from that if someone's pulling this up the ramp, the energy comes from that person's muscles, for example, and that's what gives this extra work to the box, which increases the initial mechanical energy of the box to a higher final potential or final mechanical energy. So with this problem, the E initial represents when the box is at the bottom of the ramp, and the E final represents when the box is at the top of the ramp. So we have Ki plus Ui plus work due to non-conservative forces is equal to Kf plus Uf. And let's figure out which terms go to 0. When the box is at the bottom of the ramp, it says it starts from rest at the bottom, so the initial kinetic energy is 0. And because it's at the bottom of the ramp, that means it's got no gravitational energy, so the initial potential energy is also 0. And the WNC, that is the work due to the applied force, which is that 960. The K final, we're looking for the speed of the box at the top of the ramp, so it does have a final kinetic energy. And because it's at the top of the ramp, at a height of 16 meters, it does have a final gravitational energy. So we can plug in these formulas. So WNC is equal to 1/2 mv squared final plus mgh final. Does the mass cancel out? Remember, because this term right here does not have a mass in it, you cannot cancel these two masses out. You have to have a mass in every single term, including this one, to be able to cancel out. But you can take this equation and rearrange it to get the Vf by itself. And if you solve the equation for the speed of the box when it reaches the top of the ramp, if everything was entered correctly in your calculator, you should get a final answer of 8 meters per second. In part B, the box is now entering into a state of projectile motion. So in projectile motion, the only force acting on the box is gravity, which is a conservative force. So now we can just go back to using the conservation of energy equation, which is E initial equals E final. So the E initial equal to the E final. In part 1, we want to find use conservation of energy to calculate the height, the maximum height above ground level that the box reaches. So the E initial is going to be when the box first leaves the ramp, and the E final is when the box reaches its maximum height. So let's just plug in the Ki plus Ui is equal to K final plus U final. So in this case, let's see if any of these terms go to 0. The box at the top of the ramp is moving at a speed of 8 meters per second, so it has kinetic energy. It also has potential energy, gravitational potential energy, because it is at a height of 16 meters, because that's the top of the ramp. At the highest point, don't be confused to say the velocity is 0, because remember, the box is still moving horizontally. So it does have a horizontal component to the velocity, so it does have some kinetic energy, and because it's at the highest point, it obviously has some gravitational energy. So none of these terms for this part of the problem will go to 0. So we're going to enter in all of the formulas. I can start making a shortcut now, which is that I already know that each of these 4 formulas has mass in it, has an m, so I can go ahead and just write the formulas with the m already canceled out. So I'm going to write 1/2 v initial squared plus gh initial is equal to 1/2 v final squared plus gh final. And in this problem, we want to find that final height, that's the height at the maximum height, so we want to find the HF. We know the initial height, this term right here, that was the 16 meters, because that's where the box left the ramp. We know the initial speed of the box, that was the 8 meters per second right here. The final speed, that's the speed at the highest point, which technically we don't know yet, except that we have solved it in a previous problem. Because when the box left the ramp, it was moving at a speed of 8 meters per second at an angle of 30 degrees. So if we break this into components, the vertical component right here is going to be 8 times the sine of 30, which is just 4 meters per second. The horizontal component is going to be 8 times the cosine of 30, which is root 3 over 2. So that simplifies to 4 root 3 meters per second. And at the highest point of the projectile, the trajectory, it only has horizontal velocity. Remember, the vertical velocity goes to 0, and the horizontal velocity stays the same throughout. So at the highest point, the velocity is equal to the horizontal velocity, which is this right here. So that is what's going to be plugged in for that V final. So now you know everything in this equation except for the H final. So if you just rearrange the equation to get the H final by itself and plug all the numbers in, you should hopefully get an answer of H final is equal to 16.8 meters. It's worth going through the math and trying to put all this in your calculator just to make sure you get the right answer, because I just don't want to see people losing points from making calculator mistakes on a test when you understand all the physics and all the math behind it. So try and go through and rearrange this equation for the HF and plug in everything and just make sure that you get that answer of the 16.8 meters. And it says use conservation of energy to calculate the speed of the box just as it hits the ground. This is actually a nice, easy one to finish up on. The initial energy is equal to the final energy. We're still going to take the initial energy to be when the box first leaves the ramp, and the final energy is when the box strikes the ground. So with Ki plus Ui equals Kf plus Uf, the initial kinetic and potential energies, neither of them are 0, for the same reason they weren't 0 up here. The box is moving at the top of the ramp, and it has height. when it hits the ground, it is moving just as it hits the ground, so it does have final kinetic energy, but as it hits the ground, it's got no more gravitational energy because it's got no height to it. So we can knock off that last term and say that UF is 0. Do the same thing as before, plug in the formulas, go ahead and leave out the mass. So 1/2 V initial squared plus GH initial is equal to 1/2 V final squared. And this is an easy one to solve for because you just want to get that V final by itself. Remember, kinetic energy and just energy in general is a scalar, not a vector. So you don't have to worry about doing things, breaking it up into horizontal and vertical components. When you solve for this VF, that's going to be the total speed, which already takes into account the horizontal and the vertical parts. So plug in these numbers. Remember, VI is the 8 meters per second. The HI is the 16 meters. And when you solve for VF, you should get a final answer of VF is equal to 8 square root of 6 meters per second.